Transformers toy by any chance? What? Maybe one, just one or two?
Is that like a Gundam?
Like a Gundam, yeah, like a Gundam, but it's, you know,
It's better.
vaguely heard of them. You might have found one in a shop once. So our next talk, our next panel is going to be about Transformers, the toys, and a bit about the science behind them. So please join me in welcoming to the stage Josh Lurie. Engineer who's going to be telling us a little bit about about the material science of our toys and why they are the way they are and why sometimes they change the way they initially are. So without further ado, over to you, Josh. Thanks.
Right, hello everyone. Really absolutely glad to be here after 3 years, like I'm sure all of you are, and I'm thrilled to be privileged to give you all a talk. So, today, as the title suggests, it's caring for your cybertonium, a brief look into the material science and engineering of Transformers toys. And the button works. So, who remembers what the word cybertonium is from? This is the contents, so just running through what we're going to tackle today. Just in case I run out of time, I'll give the thanks up front. So thank you very much to the TFN team, and particularly to Dave Wallace. I think when I proposed the concept of the talk, it was very much a new idea, but I'm very glad that they were receptive. Thank you also, very special thanks to Gavin Spence for providing some illustrations, and to James Rose for sending through a badly sunburned toy for some experiments. Right. So, a quick shout out into the hall. What are some issues you have with your toys? So, yeah, gold plastic, clear plastic, stickers coming off, rust. So, what we're going to talk about is really more of the today, a bit more of the third one there. So, changes over time. Or changes with use is things that they wear out. Things just changing on their own, just by the nature of materials over time, or aging. And things that change over time due to external factors. So, the temperature, humidity, radiation, all that we call weathering. A little bit about me. My name is Josh. Joshua's on Twitter. I'm a fan since the 80s. I like the very big and very small. Take a few photos. At work, I'm a space engineer. I work for Airbus on spacecraft. Heavily involved in my career so far, mostly on telecommunications, satellites. But a few interesting things like space harpoons to remove space debris, some work on things like Bepi Colombo, which is going to Mercury, Rosetta, ExoMars rover, and recently the Mars Sample Return, Sample Fetch rover. Here is just a quick list of reference sources that I've used, or whether it's been directly or through just for reading to try and get up to speed with some of the topics. So feel free to check out some of those sources. Right, so for fear of time, I'll carry on. So, don't know what is a material? Shout out.
Plastic.
Yeah, plastic's material. Anyone else?
Steel.
Yeah, metals. Can anyone tell me what a process is?
Creating plastic.
What happens to materials?
Yeah, exactly. What happens to materials? So, processes and materials are completely intertwined. You can't have one without the other. And a process can be anything from what happens to materials. A process is also how you extract materials from the ground, how you process them, the process of applying paint, the process of molding, everything you do to turn into the final product every step involves a process. So, what are some different types of materials? Broadly speaking, and a lot of this is completely non-exhaustive. So, metals, non-metals, ceramics, organic materials, so all of us, polymers, composites, and more. There's things like semiconductors and all sorts of fancy, funny, newfangled things. And then quickly, just as a little high school recap, we have generally three phases of matter, which are liquid, gas, and solid. So, some important properties of materials. So, when we talk about really what affects materials in a way that affects how they last over time or how they last with usage. Mechanical parameters, so strength, we heard how strong the material is, that's how much force you can apply before it breaks. Hardness, so hardness is actually it's a relative measure of how much one material can deform against another material. And impact toughness, which is quite important to us today, which is essentially the amount of energy that a material can take such that it avoids little microscopic cracks propagating throughout. From a thermal point of view, we have melting point, so ice to water, boiling point, water to steam, and something funny called the glass transition threshold, which is where you have something like plastics, or glass in fact, and it's the point at which it starts to be, will change from a rigid solid into a more flowing solid. If you ever heard people say, oh no, glass is actually a liquid because it slowly bends and melts over time. Not entirely incorrect. Below its glass transition temperature, glass does in fact behave like a liquid. So it's called an amorphous solid. And over time, yes, the glass will slowly seem to melt. Again, I want everyone to shout out if you know some answers. What are some specific materials that we have in our transformers?
ABS.
ABS, plastic, yeah. Anyone else? Yep.
Die-cast.
Die-cast, yep.
Chrome.
Is that one over there?
Chrome.
Chrome, yep.
PVC.
PVC,
HCP.
yep. So, very fortunate for us that all of the Takara releases, because of Japanese regulations, do actually have a list of materials on their box. So we've been able to actually go and find out exactly what is in some of the transformers, at least coming from Takara. So this is a bit of a list. It's a combination from looking at MP10, which are underlined if there's a difference. The latest MP Trainbot Shuki, and MP44. So, plastic parts, so opaque, so they're not transparent, they don't allow light to flow through. There's a small selection of different things that are used. The most common plastic used for consumer products, in particular toys, is ABS plastic. So it's something called acrylonitrile, butadiene, styrene. These are all an absolute mouthful. There is screen up here as well. Polyoxymethylene, which is also called, you see, POM plastic. It's also known as acetyl. So if you see, if you have like an acrylic material, that's POM. Polyvinyl chloride, which is PVC plastic. Polyamide, PA plastic, which one of the very well-known trade names is nylon. So that's polyamide. And polypropylene, you might see as PP. Notably, down that list, the plastics are more and more flexible. So by the time you get down to nylon and polypropylene, they tend to be the sort of softer rubber parts, which they use for instance, spiky bits, which they're afraid kitties might hurt themselves on. Transparent parts are generally one of two things. Either a similar sort of cousin to our friend ABS, it's called methyl methacrylate acrylonitrile butadiene styrene, or MABS plastic. the second one, which is used on MP10's Windows, is polycarbonate. You might also know polycarbonate from things like phone cases and everything that is quite strong. Screws, pins, or fasteners, I believe most should be stainless steel. Stainless steel being steel alloy or iron alloys with at least 11% chromium, which are more resistant to corrosion. The material doesn't appear on the boxes of the Takara releases, so there is a question mark there as to whether it is actually die-cast, but I have some doubts about that. For chrome plastic parts, they are just plastic parts and they are coated in aluminium, usually by a process called vapor deposition. You put the entire mold on a sprue inside a vacuum chamber, you fire off a particle against a slab of aluminium, and the aluminium releases a molecule, or an atom, a chunk, and it flies down and it impacts onto the plastic and adheres. It forms a layer of aluminium. Shiny metallic parts. So these are generally one of two things. Either it is plastic which contains metallic pigments. So again, something like aluminium, it's very small amounts. Or it's plastic which is painted and the paint contains metallic pigments. The effect of the paints or the plastic is really dependent on the size of the pigment. So it can vary from, I believe, down to about 70 microns, a micron being 1,000th of a millimeter, all the way up to about 0.7 millimeter. And the finer it is, the more of a sheen it gives, and the larger it is, the more of a sparkly effect it gives. Colours and decals. So, paint. Paint and, applied in various ways. So again, process. So what's the difference between a paint app, a decal, or a tampograph? Nothing. They're the same material, more or less, but the process is different. So they're applied onto the substrate in a different way. Also, stickers. So stickers are either paper or metallic, so foil stickers, and they're applied onto the parts using an adhesive, so a bonding agent. Rubber tires. Again, I believe there are a few different ones used, but the ones generally used by Takara is styrene butadiene styrene, SBS, which again, you can see very common monoelements to ABS and NABS. And die-cast, and this is actually something I learned recently doing the research for this talk, is we always say die-cast, but I say, well, what is die-cast? That's not an element. So die-cast is actually something called ZAMAC, which is very, I'd say uncreatively, but us engineers like to name things with very boring acronyms, it stands for zinc, aluminium, manganese, and copper, the K being a different language version of copper. So yeah, you have die-cast parts, it's ZAMAC, essentially. You all know the warning beacon and its message. If Cybertron be your home, far away, never roam. Hear my message, listen and fear. Danger comes, the end is near. Just like us, you soon will rust. All shall be turned to dust. So, Grimlock says, let's talk about rust and corrosion quickly. I forgot to give a thanks out as well at the start to the general Transformers community, particularly on Twitter. I did give a call out for people to provide practical examples of various bits of materials, of wear and whatnot. Here, for example, in the pictures from the previous slides. So we can see here an example of corrosion. Now, rust is actually, it tends to be used colloquially in more generic fashion, but rust does explicitly relate to iron oxide. Corrosion relates to, in fact, any metal. So, what happens during rust? Well, oxygen from the air, and especially in the presence of moisture, so H2O, reacts with the metal. it's usually in an anodic fashion. So there's a transfer of charge, the oxygen or the water molecules will break, and the metallic elements will provide them with electrons, which helps to make them balanced. So that's essentially corrosion. There are a lot more, there are some other different types of corrosion. Generally, because we're dealing with things like Zamac or possibly stainless steel. I think with this trigger con, I think that might be Zamac on the pin for the wheel there. It tends to only be that simple anodic form of corrosion rather than other sort of galvanizing types. How can we deal with corrosion? Well, it's pretty easy. Corrosion basically affects the top layer of the substrate in this form. So actually what nature tries to do itself is to passivate. So nature reacts with the top layer, and the metallic oxide that forms is actually protective, so it won't go any further than that. Some metals will oxidize just in air without any heat or without moisture, like lead, forming a layer of lead oxide. But notably, the layer of oxide is actually quite brittle. It's almost like not quite as fine as dust. So yes, you can get rid of this layer by just abrading it. So a metal fiber pen or thereabouts, Scotch pad will actually get rid of it. The ways that they tend to design to protect against corrosion are, again, to passivate. So either that means they apply their own treatments to cause the creation of an oxide layer from the factory, or you seal it. So we seal it with things like paint. That's why the metal parts are in fact painted. And it's probably why Paul Megatron's feet over there tend to be a big problem with cosmic rust, because they are really bare metal. There doesn't appear to be any treatment on top of them. They seem to be just bare. So if you're keeping them somewhere, I'd probably say don't keep them next to your bathroom where the shower is turning out lots of steam. If you're able, stick some Descent in the shelf with it, and try to keep it all nice and shiny. Okay, so there are a lot of topics to talk about today, and because of the limited time, I thought I would try and hit a few of the big ones, a few of the ones which I think a lot of people would actually like to know a lot about. It so happens that all of those actually have to do with polymers, so they're to do with plastics. So, what are polymers? You know what polymers are, you use them every day. Various types of plastics. In fact, you know these types of plastics because if you look at some products at home, they'll have a recycling indicator number. That's the International Resin Identifier. Whilst it doesn't identify all of the different resin types, it does identify a lot of the main consumer ones. So, PET plastic tends to be the light water bottles, high density polythene, also spray bottles and whatnot. PVC, in its more rigid form, is used generally for actually a lot of piping, because it's quite robust from weathering. Low density, things like shopping bags, polypropylene, something either bottle caps, or sauce sachets or takeaway boxes. And then down the list, polystyrene is a very interesting one because you probably actually know it in a few different, quite different forms. Either polystyrene cup, which seems quite different to the sort of the drinking cup. And then other, we have things like, again, Lego bricks, which are ABS plastic. The ones in the middle there, I put in, I can't remember what they were. And the third one is nylon, I do believe. Okay, we can broadly then divide polymers into two types. So thermoplastics. Thermoplastics are something that, as you would intuitively think, you heat them up and they melt and they're nice and flowy, and then when you cool them down, they harden and solidify. So this is generally what we think when we talk about molds of plastic parts, they heat them up very hot, they inject them into the injection mold, and then as it cools, it hardens and forms the correct shape. So another way to think about this is the picture on the left is glass blowing. So as I said, glass is interesting because glass is a thermoplastic. When glass blowers heat it up under a flame, the glass becomes flowing and actually becomes very, very malleable. When they're able to shape it and take it off the flame, it very readily cools down and hardens. But importantly, once it's in its more liquid shape, it doesn't shatter, it doesn't crack, it's essentially, well, it's an amorphous solid, but it's like a liquid. And the second one are thermosetting plastics. And these ones are different because once they've hardened, they will not liquefy again when you heat them. They are what we call cured. So this is a bit like putting pottery in an oven. This is exactly what happens for adhesives. So it's like super glue there. So you put it on something, you let it sort of quote-unquote dry out. It's actually curing, so it's forming long chains of hydrocarbons. And in fact, for thermosetting, they tend to be cross-linked hydrocarbons. So they have lots of the macromolecules and all linked and connected up in a very strong material. Perceptor's showing us there on the bottom left. If anyone's familiar with a stress and strain curve, so if you have the unfortunate pleasure of doing 8 o'clock static dynamics for engineering at university, you recognize this, and basically it's saying if you keep applying force to a material or to a part, how much force can it take until it breaks, and how much does it stretch, how much does it deform? So interestingly, we can see the shapes of 3 very different types or families of plastics. The one in the middle is our general plastics, so if you take a nylon part or a PVC part, you keep applying force until it reaches a peak, and when it peaks and it starts to net, the cross-section changes, so the amount of force you need to deflect it drops, but it can take quite a lot of strain before it's, or elongation before it breaks. On the left we have brittle plastics, which are generally are stronger than non-brittle plastics, but they can't take any strain at all. So we imagine a clear plastic, you can apply quite a bit of force, but when you apply too much, it's not going to bend, it breaks. And finally, on the bottom, highly elastic bonds, which we call elastomers, which are things like rubbers. Some rubbers, so elastic bands and whatnot. So they can take a huge amount of elongation, huge amount of strain energy, but it doesn't actually destroy any of the bonds. So, saying polymer, what is a polymer? So, it's all from, obviously, it goes on the word. Monomer meaning one part, polymer meaning many parts. Some examples are tetrafluoroethylene, or in its polymer form, polytetrafluoroethylene, or PTFE, or the trade name Teflon. Vinyl chloride, or polyvinyl chloride, in its polymer form. And here, not using covalent bonds, but in fact using combiner bonds is abominous, and its polymer form, polyabominous. So, talking about the order of things in entropy. So there's different forms. So, glass is what we call an amorphous solid. It's like that on the right. So what happens when you form polymers, when all these, during the process, all these monomers link together, they like to form in different ways. So some are structured, they form crystalline patterns. You can see there, here there's 2 grains in different configurations. And some like to form big, long, completely random, stringy type of chains. And these we call amorphous, which means without form. Generally, the crystalline ones are weaker. They tend to be ductile, so again they can take a lot of strain and they're malleable. But they tend to be opaque. So the reason why they tend to be opaque is that the refractive properties change. The interface between grains of the materials, when the chains change their geometry, the light tends to reflect rather than transmit through, and that's why opaque plastic is opaque. Amorphous tends to be things like our clear plastics, so polycarbonate or MABS, and what happens is the very random form allows light to pass through, and that's why they are clear. So a few small things that can happen. I mentioned the term cross-linking before. So this is cross-linking. So when two chains decide to form up and form links between them. And when they form together, they are stronger, but they are also more brittle because of these extra links. The chains aren't able to slide relative to each other when you apply a force. Instead, they want to try and break. We also have chain scission. So during some chemical reactions or when molecules receive a certain amount of energy, what happens is that the chain breaks. The end molecules on one side and the other side essentially get enough energy or a different reaction that allow them to change the bonds that they have, and you break one chain. Reactions are radicals. So a radical is anything which is able to have a reaction. You might have heard the term free radicals. So a free radical is a radical that's just floating about, ready to cause havoc. As we can see here, we have some constructicon radicals, an ambulance radical, we have this nautilator radical, which have decided to take away symmetwin and replace them inside our molecule of polyatomics. And we can see this changes the colour of that molecule. So, now we've got some basics down. Clear plastic and stress marks. In fact, I've got a very good example sitting on the table afterwards. I've mentioned already about the different natures, the crystalline nature versus the amorphous nature. So yeah, what I've taken a look here is I've actually looked at some of the recorded material properties for both ABS and MABS. So very similar chemical structures, but we can see that they can take quite a lot of different amounts of strain, energy, elongation, and stress. In fact, MABS can take, I think it's about 15 or so higher megapascals at yield and at failure. And ABS, so the opaque version, can actually stretch up to 50%, so almost double at failure than compared to MABS. So this is quite illustrative. If you apply the same amount of force, your opaque plastic is going to stretch, and your clear plastic is going to break. It's a good example of the picture on the top left. You can probably see at the top of the cockpit, it looks white. That is because when you break the clear plastic, the open bonds do react with other free radicals and can cause a chalk-like substance to evolve. So, stress marks. So we have our opaque, we have our transparent, our crystalline and amorphous types. And what happens with a stress mark? So if we look at the left, we can see I've got here a bit of red plastic. So all of the colours, violet plastic? I'm very colourblind. You have a colour of plastic here. All the other colours get absorbed, do not reflect to the eye. When you deform it, what happens with the crystalline types of plastic is you pull them and the chains start to unravel. So they slide against each other, but still try and maintain as much as they can the structure. And what happens is by changing that structure, it changes the refractive properties. And suddenly, all of the colours in the spectrum are not being absorbed, all of them are being reflected. And if all of the colours along the visible spectrum are being reflected and meet your eye, that is white light. And that's why stress marks look white. The same, we have probably examples of different plastics across this range, but generally for amorphous types, it prefers to break, like you can see there as we discussed just before. Gold plastic. So I mentioned metallic pigments earlier, and can see on the top right a few different geometric forms of pigments. There's flakes, sort of platelets, and spherical, lenticular. And as I said, the pigment size can vary from circa sort of down in the kind of tens of microns up to hundreds of microns, so a huge different range. Now, remembering that atoms are down in angstrom scale, they are very, 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 very small. And essentially what happens is you have these incongruities, these discontinuities in your plastic matrix. So like you can see, we have aluminium there sitting between 2 grains of opaque plastic. Now between those grains, there can be voids. Voids mean, especially between 2 grains, you can form a crack. Stress loves to build up at interfaces. So that's why plane windows are circular and not without corners. And apologies, I have got this in the text the wrong way. The coefficients of thermal expansion are actually the opposite. Plastic does expand with heat about 4 times or so more than metal. So if you were 1 meter of aluminium, it will expand by roughly 20 microns per degree Celsius, whereas ABS will expand about 80 microns per degree Celsius. So what happens, say if you heat this up, the plastic is going to expand a lot more than that pigment particle. And as it does that, these little cracks all throughout the material propagate. They grow insidiously. And then, as you cycle, so if you take it back down and cold and up and so on and so forth, it gets worse and worse and worse. By the time you apply a force, so you're handling it, so you're transforming, that's enough, and the cracks which are spread throughout fail. So when we talk about earlier toughness, impact toughness, so that's where gold plastic or metallic plastic, it has a very low impact toughness. So it is not able at all well to handle formation of cracks. So just by heat alone, if you live somewhere where you might have a hot summer and a cold winter, give it a few years, give it a few months, yes, on its own it will degrade and may actually crumble by itself. So this is also one of the big ones. So yes, the key question, as my partner says, why, it's a question of 6 months, why is there a lateral flow test taped to your window, Josh? Because I was conducting an experiment. Many months before I actually approached the TF stuff, I think there was a lot of talk going on Twitter because there were a lot of incidents of recent figures coming out of the box with quite bad yellowing. A lot of people discussing the question around why it was occurring. I thought I would try and do an experiment that would be quite illustrative. This one with in mind of best practice and trying to get that across. So what I did is I took a humble little level flow test. I took out the strip inside and I taped it to the window for 6 months and watched what it would do. So I'll talk about it in a slide to come. So, what causes yellowing? The sun. The sun produces electromagnetic radiation, which we all know and love, because it contains things like visible light, which is how we're all seeing each other right now. But above visible light and below visible light on the spectrum, there are other types. Now we can see, as you go to the right, the wavelength increases, but conversely, the energy decreases, the ratio being the speed of light. And towards the bottom, so from visible light we go through UV, ultraviolets, down through X-rays, gamma rays, but also outside of the Earth we have other sources of high energy particles, cosmic rays and whatnot. And those tend to be what we call ionizing radiation. They are very energetic, that is to say, they have enough energy to cause an electron inside a molecule, inside an atom, to jump from one valence state to the next. So importantly, not all the UV from the sun comes through. Within the UV there's a range. We identify 3 bands called UVA, UVB and UVC. You've probably seen from sun cream blocked by the atmosphere and doesn't reach us at all. UVA and UVB, because of the different wavelengths, do reach us to different amounts. UVB actually is able to better penetrate the skin, which tends to cause things like sunburn, compared to UVA, which is slightly less energetic and would more sort of giving you a tan rather than anything. Just for some illustration, I took a look and I tallied up some numbers. So, according to the UK government, on average, any one of us receives about 2.7 millisieverts of ionizing radiation per year. In the US, that's 6.2, interesting enough. If you're a spacecraft in orbit, you receive 100,000 millisieverts per year, so quite a lot. And just out of interest, every time you get a dental X-ray, it is 0.005 millisieverts. Transatlantic flight, as you're higher up in the atmosphere, is 0.08 millisieverts. But the point at which it starts to get hazardous to health is about 100. So you're all very safe unless you work in a high radiation environment, like nuclear power stations, or if you work in radiography or whatnot. So, a bit of a hardcore chemistry. There are a few steps. The yellowing of plastic is actually quite an involved process. It doesn't just happen in one shot. So ABS plastic, as an example, so it's made of three components in the monomer. Acrylate, acrylonitrile, butadiene, and styrene. So it happens first in the butadiene component. The high energy, so the UV light, encounters it, and in the presence of oxygen, it breaks a bond. So where usually there would be the carbon which is next to a nitrogen atom in the chain, it decides to dump part of that connection, and it reacts with the O2 and forms oxygen and hydroxide functional group. What happens then is that group is actually unstable, the OOH, so it decides to break down on its own. And what it does is it releases a hydroxide, so the OH, which is now a free radical, ready to cause mayhem. Now the free radical passes along and encounters the styrene part of the molecule. Now styrene contains a benzene ring. So benzene is like a hexagon with 6 carbon atoms with a double bond, single bond, triple bond, etc. What it does is, through a series of about 4 steps, it starts to react and it breaks down that strong benzene molecule, that function group, and in the end results in something called 2-hydroxynucleic acid, or nucleic acid for short. Now the important thing about nucleic acid is through its shape, so you can see it has a single bond, a double bond, a single bond, a double bond, a single bond, and a double bond. And that is something called a conjugated bond. And because of the vibrating frequencies between the atoms across those bonds, conjugated bonds will absorb everything except for yellow light. So what happens is, by the time you have nucleic acid in your plastic, it has become yellow because it is only reflecting or transmitting yellow light. Now, it's often not too obvious. The appearance of most plastics, particularly ABS, before you put in any pigments, you probably know the term like a grey prototype. That is the colour of plastic. So you can imagine, if you know that when that yellows, it's fairly obvious. Right. So luckily, I already had an experiment done when I moved into my flat. These are mounts for a set of blinds on a bedroom window. They're made of ABS plastic. They were on the window for 6 years. And what can you see? So you can see the areas where the sun didn't reach are beautiful, white, pristine plastic. The areas where the sun did reach are extremely badly sunburned yellow plastic. So it's already quite illustrative about the effect of sun, direct sunlight over time. Well, I would say never keep a transformer on your windowsill. But more importantly, section from it, and cut out a little bit. Ionizing radiation in UV only affects the surface layer. It can't penetrate at all. It's a matter of microns or less. So the section which I cut out, you can see inside it's actually perfect still. You can't even with the eye see the thickness of that sunburnt layer. It's so thin. This is why some people might suggest to you that to remove yellowing you can braid. And yes, that will work, but you'll change the form of the plastic. Yeah, so at this point it was about 9 years of exposure. So it's quite a good amount. So, our lateral flow test. I had one, which was a control sample, which was on a dark shelf. Well, no, two. I had one in a dark cupboard. The second one on a shelf, which is in a light room, but not in direct sunlight, which is the top left picture. And then the experimental one, which was on the windowsill. And then importantly, half of it I covered up with aluminium foil. I wrapped it several times. It had an effective aluminium shielding of 0.2 millimeters, 200 microns. Whereas the other side was untouched. And in the middle, I painted it using just some Warhammer acrylic white paint. And what you can see is very illustrative. So over a period of pretty much exactly 6 months, the changes are quite evident. So this was not an experiment to show how robust your lateral flow test is. It's an experiment to show the differences in how you store your transformers or other plastic toys. We can see the very exposed one, so the one on the right at the bottom, is relatively very yellow compared to all the other samples. Interestingly, with just this tiny amount of aluminium shielding right next to it, it is far better. So it's much, much better. And whilst you shouldn't necessarily have to wrap all your transformers on your shelves in aluminium foil, it is really illustrative if you are perhaps storing things in a box. It's not a terrible idea to wrap the box in a couple of layers of aluminium. Right, so quickly, how does hydrogen peroxide repair yellowing? So a tiny bit of chemistry. It's important here to remember that actually this doesn't reverse the damage. It is a repair. So it doesn't reform the ABS exactly how it was. How it works is that it provides an oxidizing agent. Hydrogen peroxide, H2O2, has all the good things of that. It's got the oxygen, it's got the hydrogen. So by the same means, you put your part in an amount of liquid hydrogen peroxide, and very counterintuitively, you put it back in the sun. And you might guess why we do that, because like the initial reactions that damage your plastic, it requires energy in order to unmake the H2O2 and donate the various atoms and the electrons to share with the polymer. So how it works is essentially the hydroxide replaces some of the functional groups on that nucleic acid. So you can see there, so in the two in the middle, it's replaced just carbons with a double bond, or single bond, sorry, between them, with hydroxyl groups. And what we can see now is instead of being the conjugated bonds, we now have all single bonds. So what that means is it no longer absorbs all the non-yellow colours, it now retransmits everything again, and that's why it is now white again. So you don't repair the plastic, well, you don't reverse the damage, but you do repair how it looks. And interestingly, this is the exact same thing that happens if you bleach your clothes. So I think it's lipines, which are the colorant in ketchup. You have that on a white shirt, you apply bleach. This is the process that goes through. So again, it doesn't get rid of the stain, it just makes the stain appear to the colour you want it to be. And in final time, so best practices, further topics. So hopefully you picked up a bit of this from the previous slides, but I'll run through them. So number one cardinal rule, don't keep your figures in direct sunlight. Please. I see photos of things, of white figures or gold plastic figures sitting on sunny windowsills, and it makes me ache. Keep them at a distance from UV lights. The distance means preferably more than 1 meter away. like I say, the dosage from UV lights is relatively small, but it does contribute. Whether that has an effect on figures in shops is TBC. It's got a long amount of exposure time. And same for you. If you're at work or not given UV lamp, it's probably actually best practice not to be too close to it. Keep them at cool temperatures, so don't provide them with more energy. But keep them at constant temperatures. So if you have them up in the attic changes in summer from 40 degrees down to 0 degrees in winter. That is quite a large temperature change to cycle through. Materials don't like it, perhaps propagate, and the material will break. So you usually see things say store in a cool, dry place. That's it. Keep them safe from shelf dives. Yes, everything likes to break when it falls because these things are not metal. Generally, they are plastic. Generally, they have enough weight in the figure themselves to overcome the strength of various joints. So, put a rating up. And away from cigarette smoke. So I haven't covered the cigarette smoke, but cigarette smoke, as you know, causes yellowing, although it tends to be a combination of the smoke materials, which do actually have some yellow colour to them, as well as the materials in the smoke, which are all products of that combustion, do also provide a reaction that causes the yellowing process. Storing your figures. If you have painted figures or chrome figures, store them individually in plastic bags. If they rub against each other, all the treatments, so the chrome and the paint, it doesn't like it at all. So it's called fretting. So plastic means that only the plastic bags will rub against each other, and hopefully that the figures don't. Most of the plastics, especially the general type of bags you get, like polythene or polypropylene, have very good friction properties and should not abrade your figures. Like I said, if you're doing long-term storage and you have a spare roll of alfoil, it's not a terrible idea to wrap the container in a few layers of aluminium foil. In fact, I was looking at my Detolfs the other day, and my Masterpiece Prowl gun and its shoulders, which are both nylon parts, are starting to yellow, so now I'm thinking I should back up my Detolfs in a layer of shielding. And if you have parts which have things which might be sensitive to humidity, put in some desk mat. It is hazardous to health, so keep out of reach of children and pets. Cleaning, use a soft brush, like a makeup brush, because it will get rid of the dust, and it's non-abrasive. Don't use air sprays because they can strip paint. Transforming, so using your figures, don't apply too much force. If it feels like it's going to break, and it feels like it's too much force, it probably is too much force. That's not always the case, especially with Titan class stuff, but always ask someone if you're not sure. And when applying stickers, always clean the surface first, because there's lots of things like fingerprints especially, which have oils which try and stop adhesives from sticking. Further topics, stuff I didn't cover, rubber ties, breaking, disbonding of stickers, dust agglomeration, loose joints, chrome wear, all the rest. Please contact me on Twitter. What I'll do is I'll make a thread with everyone's questions. I'm happy to answer them outside of this, of TFN, and onwards, so please send me questions if you want. And then just a slide showing some of the recent incidents of early yellowing. There's not enough time to go into this. I do have some thoughts about why this is the case. Ask me on Twitter or come to the bar, we can have a chat about it. So thank you everyone. This is probably the most intense science talk I've seen at TF Nation. But I feel like it's really good information for everyone to learn, and maybe it can help you think about how the toys work.
Because you've finished literally the minute on time. We probably have got time for just literally maybe one or two questions, because we've got a bit so let me run and do a couple of questions, and then we'll give you a little bit of a break before the next panel. Quick question over here.
Hi mate, when a figure starts yellowing, is it true that even if you you then take it away from any sources and cool it, the process will carry on?
Yes and no, more than no. As soon as you've taken away the energy source, the light, it will stop the butadiene from degrading. But the reason why they say it carries on is that those free radicals that were already generated will still remain in it, so they will start, until they get used up, they will keep on reacting with styrene to cause it. But generally, once you take it out of the sun, you prevent any further degradation from happening.
One at the front.
Hi. For the yellowing as well, is there any way that you could view the figure visually, like with glasses or something, and you don't get that effect if it's just it being reflected back to us?
Good question. I would imagine so. I'm not an expert on optics, but I would guess that there's some type of like polarized lenses that might be able to do that, or some type of color filter. But it's good. Yeah.
Okay, any more? Anyone for any more? Okay, one last question.
I'm cheating, I've got 2 questions.
Oh,
It's a two-part question.
Good stuff, Josh. Honestly, it's amazing. If you were my science teacher, I would have been a happy boy at school. So 2 things. With the stress in plastic, if you use a hairdryer, it gets rid of the stress mark. Why? And my follow-on, I cover my storage boxes, which has all my G1 boxes in there and stuff, with like a car cover to block out the light. Is that the same as
Yeah. So, in fact, I don't know if I mentioned it, but the main pigment used in white plastic is it's titanium dioxide, which is called titanium white. In fact, the reason I mention it is because it's used in things like sun cream. So one thing that happens with titanium white, and particularly why plastic yellows more, is that the pigment itself can break down, and it releases more free radicals that actually accelerate the plastic matrix degrading. But the point is, it does that because the titanium white pigment absorbs and breaks down. It's good at absorbing radiation. That's why it's used in sun cream. So for things like card, which contains pigments, yes, the pigments in the card itself will act as a shield, not because it reflects the radiation, but because it will absorb it and it will damage the card, but not hopefully what's underneath it. Heating for stress marks, I've seen yes and no. If you have any experience saying it works well, that'd be interesting. I don't see any reason why, if you were to effectively melt the plastic or cause it to go underneath the glass transition, above the glass transition temperature, and if it becomes slightly liquid, it should be able to reform some of the grains. I don't see any reason why it shouldn't be able to do that, but I've not seen any proof that it works.
I've done it once, and it did work.
Okay.
It was dark plastic though.
Yeah, that's
just a
right.
hairdryer.
I mean, generally, if you apply enough force that perhaps it hasn't formed as much of a white mark, but is definitely bent, because thermoplastics do melt with heat, you run it under a hairdryer, or if you've got like a solder gun, something you can really heat it up, you can relax the stress, which will help keep the part nice and strong.
great.